So good morning. That is stress. Okay. The stress is nothing but the force of the resistance per unit area offered by a body against deformation is known as stress. Okay. Or similarly, the external force acting on the body is called the load or force. The load is applied on the body when the stress is induced in the material of the body. Okay, that is nothing but stress. Okay, when you apply the external load, there should be a internal resistance should be taken in between the body. That internal resistance is nothing but stress. Okay, so the notation for the stress is sigma, and the formula to find out the stress is load per unit area. That is, the area is nothing but the cross sectional area of the material. Okay, that is nothing but stress. Okay, so similarly, the unit for the stress is Pascal. Okay, then nothing. Next one is the strain. When the body is subjected to some external force, there is some changes of different dimensions of the body. Okay, when you apply the external load on the materials means, okay, there should be a longitudinal stress. Longitudinal strains means, okay, when you apply the load on the axis of the body is tends to move in its axial length. Similarly, there should be a deformation of the body. Okay, that deformation is due to the external applied load. Okay, that deformation of the body to its original length, that is nothing but strain. The strain may be classified into tensile strain, compressive strain, volumetric strain, and shear strain. Okay, these are the types of strains. And next one is the types of stresses, that is tensile stresses, compressive stresses, shear stresses. Okay, this is nothing but the types of stresses. And this is the shear stresses. Okay, the shear stress nothing but the stress is induced in a body when subjected to two equal and opposite forces which are acting tangentially across the resisting section. Okay, this is the shear stress. Okay, this is the body, this is the applied force, that is P. Okay, there's the stress is induced tangentially, that is obviously parallel. Okay, that is parallel to its original position. Okay, that is shear stress. Okay, and next one is the strains. Okay, the Hooke's law. The Hooke's law, you already know that the Hooke's law, that is the ratio of the stress to the corresponding strain within the elastic limit. Okay, that is nothing but Hooke's law. The next one is the more elastic constants. That elastic constant is nothing but modulus of elasticity, modulus of rigidity, fact. Okay, then Young's modulus. Okay, bulk modulus, then Poisson's ratios. Okay, these are the elastic constants. Okay, first of all, discuss about the modulus of elasticity. The ratio of the tensile stress or compressive stress to the corresponding strain in, okay, that is nothing but Young's modulus. And the modulus of rigidity is nothing but ratio of the shear stress to the corresponding shear strain. The ratio of the shear stress to the corresponding shear strain, that is nothing but modulus of rigidity or shear modulus. It is denoted by C, G, or N. The ratio between the shear stress to the shear strain, that is nothing but modulus of rigidity. And the fact of safety, the ratio of ultimate tensile strength to the working stress. Okay, that is nothing but factor of safety. Okay, the next one is discuss about that longitudinal strain. The longitudinal strain is nothing but when a body is subjected to an axial tensile load, there is an increase in the length of the body. There is an increase in length of the body. At the same time, there is a decrease in other dimensions of the body. Okay, when you deformation take on rod. Okay, the rod is in circular cross section. When you apply the axial load, automatically the diameter will be reduced. Okay, the length will be increased, and automatically the diameter will be reduced. That diameter is nothing but the lateral dimensions. Okay, then lateral strain, the ratio strain at the right angle to the direction of the applied load, that is nothing but lateral strain. Okay, then Poisson's ratio. The Poisson's ratio is nothing but the ratio of the lateral strain to the longitudinal strain is nothing but Poisson's ratio. Okay. Then similarly we have discussed one problem in this unit, and see, this is the find the minimum diameter of the steel wire which is used to raise a load of 4000 newton. Okay, we have to find out the minimum diameter of the steel wire. Okay, and the load is 4000 newton, and the stress in the rod is not to exceed 95 meganewton per meter square. Okay, that is megapascal. The unit is given as a megapascal. Okay, so you have to find out the what is the minimum diameter of the steel wire required. Okay, for that load and for that stress. Okay, the whatever the data is given means the load, applied load is given 4000 newton, and the stress is given, that is sigma value is given, that is 95 meganewton per meter square. Okay, the diameter, we have to find out the diameter of the wire. Okay, we already know the formula to find out the stress, that is stress is equal to load by area. Okay, the wire is nothing but that is a circular cross section. Wire is in the circular cross section, so you have to find out the diameter of the wire. The formula to find out the circular cross section, the area to find area is nothing but pi by 4 d square. So okay, so you have to apply the formula and find out the final answer. For that answer is 7.32 mm. This is the required diameter for that applied load and stresses. Okay, so we need this 7.5 mm diameter of steel wire is required for that application. Okay, so next one is the find the Young's modulus of the brass rod. You have to find out the Young's modulus, that is E. Young's modulus is nothing but ratio of the stress to the strain, that is nothing but Young's modulus. Within their body is within the elastic limit, you have to find out the stress. Okay, Young's modulus of the brass rod of diameter is given, that is 25 mm, and the length is 250 mm. Okay, when it is subjected to a tensile load of 50 kilonewton, the load is given 50 kilonewton, when the extension of the rod is equal to 0.3 mm. The extension is nothing but change in length. Okay, the extension is nothing but change in length. So you have to find, so what is the formula to find out the strain means? The strain is equal to change in length to the original length. So the change in length is given in the sum itself, that is 0.3 mm. The original length of the rod is 250 mm. Okay, so the two data is given. So from this you have to find out the strains, and the ratio between the stress to the strain is nothing but Young's modulus. Okay, the diameter of the rod is 25 mm. From the diameter you have to find out the area of the rod. Area of the rod you have to find out by using this formula, pi by 4 d square. By using this formula you have to find out the area of the rod. See here, so stress is within the load by area. The load is 50,000 and the area is 490.87. The formula to find out the area is pi by 4 d square. The diameter of the wire is given in the sum itself. Okay, from that you have to find out the area of the diameter rod. From therefore stress equal to 101.86 newton per mm square. Therefore strain is equal to change in length by original length. The change in length is 0.3 mm, is already given in the sum itself. The original length is also given in the sum, that is 250 mm. The change in length to the original length is 0.0012. Okay, that is called strain. The strain, it's having no unit. Okay, therefore the Young's modulus is equal to stress by strain. Okay, so by using this formula you have to find out the Young's modulus. Finally the Young's modulus for the materials is 84.883 giganewton per meter square. Okay, so this is the actual formula to find out the sums. Okay, so the next one is that analysis of the bars. Okay, this is the analysis of the bars of varying cross section. Okay, so see this here, this is having the different cross sectional. In the section 1 it's having the area A1, the section 2 it's having the area of A2, for section 3 it's having the different diameter. Okay, so different area for the different cross sections. Okay, how will you find out the deformation of the body? Okay, that is the analysis of bars of varying cross sections. Okay, so see here in section 1 it's having the area of A1, A2 and A3, different area, and also the length also. What is the length of section 1 is having the area length L1, section 2 is having the length L2, and this section 3 is having the L3. Okay, but the two directions, see the axial length, the P, the load is applying the axial direction, the load will be same. Okay, for this you have to find out what is the total deformation of the body. First you have to identify for different cross section and different cross sectional length. We have to identify the what is the cross sectional different, how the body will be deformed when you apply the load. Okay, for the different cross sections and different length. Okay, for using this to analyze this thing. Okay, for the section 1 is having the load is equal to load by area A1. For the section 2, that is load divided by area A2. Section 3, load divided by A3. Similarly for the strain already know Young's modulus is equal to stress by strain. Therefore strain is equal to stress divided by Young's modulus. The stress is load by area. Already Young's modulus is here. Okay, P divided by A. Similarly for the section 2 and for similarly for section 3. Okay, that is P by A2E for section 2, P by A3E for section 3. Okay, the strain change in length of the section 1, that is divided by L1. Okay, therefore we have to apply the formula strains here. Therefore finally PL1 by A1E, for this is the total this is the strains of the section 1. Okay, this is the strains of the section 1, stress by Young's modulus, PL1 divided by A1 E1. Similarly for the section 2, the strain is PL2 by A2 E2 E. For similarly the section 3, PL3 A3 by E. Finally the total change in length of the bar is section 1 strains, section 2 strains, section 3 strains. Okay, finally the load and the Young's modulus are similar because there is only one material, there is not a composite material, this is only one material. Therefore Young's modulus should be same, and also for both direction the load should be the same one. Therefore P and A is taking the common thing. Finally L1 by A1, L2 by A2 by L3 by A3. Okay, so this is the formula to find out the total deformation of the bar. Similarly, there should be a composite materials, means Young's modulus should be vary. Therefore Young's modulus should be vary for different section because there is a composite section. That's why the Young's modulus also should be vary. Therefore for the Young's composite section, the change in total deformation of the body is P equal to P divided into L1 divided by E1 A1 plus L2 divided by E2 A2 plus L3 divided by E3 A3. Okay, thank you.